Okay. I wanted to do a recording of homework 4 problem 1. It seemed like some students were struggling a little bit with the software, and the point is not to struggle with the software or to make this somehow mysterious. So the point is to actually learn it, and to learn it, you actually have to repeat it, building the model several times. So I'll provide a video here of me basically performing homework 1 in its entirety, as hopes that it's a resource that you can use to repeat building the model several times, once with this video, and then maybe once trying to do it again without the video. Okay, so what is our design? Our problem? Our problem is to perform a topology optimization on our beam design problem. And the very first thing we have to talk about is our process, which step 1 is define the problem. And so we have to create our design space. Our design space is going to be a 50 by 50 cross section along a 210 millimeter length. And so we're going to apply 18 kilonewtons on that in an appropriate way, with simply supported roller supports on the bottom, and using this generic FFF polymer material. Um, okay, and so that's the problem we're trying to solve. And so what is step 1 in our linear process? It's create the geometry. Okay, so let's come over to HyperMesh here. And a couple of things just to set up, to make sure we're all set up. I would right click in the white space, go to configure browser, and make sure that this show entities under subfolders is on. And the next thing I would do is go to preferences, and then I would go HyperMesh appearance. And then if you scroll down to loads, make sure that it says pixel-based scaling is on. So that will just make things a little nicer. Okay, those are kind of there's a few other configurations, but largely those are the two that will be most important. Okay, now that we're set up, let's create the geometry. We create geometry under the topology ribbon. Actually, in this case, sorry, I'm going to create geometry under the 3D ribbon because I can create 3D solids right there. And what I'm going to do is just create a 50 by 50 by 210 box. And so if I click into the solids tool, I can build different primitive solids. I want to build a box, and I want to build it in the XY or the YZ plane, so I can extrude it along the X and the length. So I'll snap into the YZ plane. I'll just click and drag to draw 2 points, and then I'll rotate around, and it'll give me the third one, and I'll just click anywhere to start with. So I know that my box is going to be 50 by 50 by 210. And when I do that, it zooms out very big, so I can fit my screen with the fit button. And right now, I don't know exactly where this is positioned, so I can hit this little position box, and it tells me the center of this box in all directions is at a particular coordinate that I don't want. I want that center point to be at 0, 0, 0, just so I know certain dimensions. So I'll center that at 0, 0, 0, escape out of that tool. I'll escape out of that tool, and I'm still in the tool, the box tool, so I can escape out of that tool, and I have my geometry. Okay, a few more things we have to do, because I need kind of let's say face edges at certain places. I'd like to have some face edges at my roller support, so that I have nodes at my roller support exactly. And I'd like to have kind of face edges where my load is going to be. So the way I do that, I think the easiest, there's many ways, but I think the easiest is to go to topology ribbon, and just to create a couple points at specific locations that I know I need things. So you can see that I'm going to create, it'll snap to lines, and it'll just say on. And I want to create a point on this edge somewhere. So I'll just create it on the edge. And it gives me the coordinates on that edge. But I know that I want this at exactly minus 100, because that'll put me at exactly where the roller is. And so when I hit enter, it puts that point right over to that position on that line. And same thing here. I'm just going to put it anywhere to start with, and then I wanted at positive 100. And then I want to create ones for the loading block. So I know that this one's got to be at minus 12.5 in order to get 25 spacing centered through the halfway point. And I know that this one's got to be at 12.5. Okay, so I've created those and I can escape out of this. I'm still in the tool, so I can escape out of the tool completely, and I have a few points. Well, now I need to make trims. I need to trim this solid so that it has edges where I need them. And so we'll go into the trim tool on the topology ribbon. And here we get a lot of options, but the option that we want is we want to split. And then what is it we want to split? We want to split solids. Then I can pick the solid. And how do we want to split solids? I can click it again. I want to split it with a plane. Now, it'll snap to all kinds of points here, but it'll also snap to points that I made, which is why I made the points. So I want to create a trim right there, and I'll go ahead and play that. And then I can pick my solids again. I just need this part of the solid, and I want to do another plane, and I'll just go down the solid here, pick the solid, and then say plane, and then snap to the point. Okay, let me do this last one. Okay, one last thing that I do is, and I didn't need a point for this because it automatically snaps to midpoints, as you see here. So I'm going to pick solids again, but I'm going to pick all of the solids. And then the plane, I'm just going to snap it to the midpoint along the length. I want it cut right down the middle there. And now I kind of have edges everywhere I need things in order to apply boundary conditions. Okay, I'm going to escape out of this tool a couple of times, and I have my solid that has been sectioned up. And you can see that it produced all the different solids here. To me, that's the easiest way to do it. There's many other ways, but that's a reasonably fast way to do it. Okay, so now I need to mesh the problem. So I'm just working down our process sheet. We're going to do meshing under the 3D tool. We're going to be doing mapped meshing. It says pick mappable solids, so I'll just go ahead and pick them all. And then it gives me a mesh size. So this is, I know that from the edge out here, that's 10 millimeters, or sorry, 5 millimeters. I probably want 2 elements there. So that's kind of how I set it. So I want 2.5 millimeter size elements. That's a reasonable number to mesh this. That isn't too fine, but not too coarse. Okay, so it kind of pre-meshes it. You don't really have to worry about most of this, but you just have to hit the button mesh for it to actually go and finish the mesh. And it finished that mesh. And I see now that I have elements. I should only have 3D elements hex 8s, and they're all going to be sitting in there. Okay, I want to escape out of this tool. Very good. Now I need to create materials. And so we'll come back here, and my material definition is here. I'll just collapse all this so you can see that we're going to create a material. I usually call it FFF polymer. And we got what, 2000 MPa, Poisson's ratio of 0.35, and a density of 0.013 grams per millimeter cube. So that's in consistent units. And then to be consistent in millimeters, grams, and MPa, my load has to be newtons. So I have to, when I go to do loading, I have to change that 18 kilonewtons into 18,000 newtons. Okay, but I got that part done. So let's work down our process. I need to create properties. So create a property. I just call it solids. Call it anything you want. We know we need to switch this to a P solid because we have solids, and the only thing we have to pick is materials. So I'll pick my FFF polymer material. Okay, I've got my properties defined here now. I need to assign those properties to elements, so I can select the property, right click, and say assign. The tool comes up, it automatically selects the solid I had highlighted, but I want to change this. If it's in components, you want to change it to elements, and you want to select all of the elements and hit play, and that will assign it. If it's assigned it, you'll see it takes its color correctly. Then I can escape out of that tool. Okay, now I need to do boundary conditions, so let's collapse all of this, and we're going to do constraints and forces, and I'll go back to this picture to show. So let's start. Actually, I will color this. I'll select the component, and I'll just rename this as design space. just so it has a meaningful name, and it'll recolor it because I selected it. To create the boundary conditions, what do we need? We need load collectors, these folders that we put things in. So I need to create a load collector for constraints. And I always color my constraints red. It's a kind of a habit. And what we want to do is we want to work on the bottom here because my rollers, my simple support rollers go on the left side here on this edge and on the right side here on this edge. So we're going to work on the bottom here while we're doing this. So rotate it around. And to do boundary conditions, I need to go to the Analyze ribbon, and then you'll see constraints. Okay. First thing I need to do is pick the left line of roller nodes. So the easiest way to do that when I'm in the node selection is to hit the 3 dots and to use the bypath option. And it probably says follow edges for you. Uncheck that because you don't want to follow edges. I want it to go straight across. So I'm going to pick the bottom node and then the top node, and you see it automatically pick them all along. It's just a fast way to pick them. It's called bypath. Okay, I got the nodes that I want. And now what degrees of freedom do I set on that line? So clearly solids, you can't apply rotation. So DOF456, which is rotation XYZ, are gone. I know I need to fix Z, right? So this is sitting this way, right? And so I know Z is supported, so Z has to be fixed. And I don't need a Y right now. Well, I know that I need to take out rigid body rotation. So Z is nothing to do with rigid body. That's being resisted by the roller. But I need to take out rigid body rotation. So I will fix this whole line in X. Because on this side, I'll only fix Z. I won't fix X so that it can move freely in X. So it's just an easy way to do rigid body. So when I say create on this side, I did X, which is DOF1, and Z, which is DOF3. Okay, but I still need to fix, for rigid body, I still need to fix a Y. There's nothing keeping this block from flying off in the Y direction. But I want it to be able to shrink in the Y direction freely. So to do that, all I do is I pick one node and I pick just the center of the roller and I say that center node can not move in Y. Just basically telling the roller, hey, you can't go off, and that's it. Okay, now we can do the other side. And I'm going to pick my nodes by path again. And this side, we're only going to fix in Z. Okay. And so if you zoom in here, you probably should be able to see some, you have to zoom way in. You can kind of see some numbers. I'll close this out. Maybe if I color this husky purple, it shows up a little, or maybe not. Kind of hard to see, but that number is just a 3 there. Sometimes you got to go into wireframe if you want to see it, but or even, yeah, wireframe. And I got to turn off the geometry. There we go. So now you can see the 3. So let me just explain that a little more. I don't like wireframe visualization, but if I have to see numbers, it's a good thing. So let me turn back on the shading. You can play with the various visual. This is where to visualize. You can also visualize up here. So you have all the finite elements and all the geometry, right? So if I turn on the geometry, you can see the geometry. If I turn off the geometry, I can turn on the finite elements. I see just finite elements. If I turn both on, I see the geometry and the finite elements overlaying each other. So this is just a really easy place to control kind of globally visualizing the finite element or the geometry. Realize that right now I have both. That's why I'm seeing the edges, which is a nice thing because I can apply things on edges and it will automatically pick the finite elements behind it. But know that you can turn off the finite elements behind it, or you can turn off the geometry behind it, and or both, along with various visualizations down here that you can pick. So just kind of know that that's where you do visualization stuff. Okay, where am I at? We did our boundary conditions. Now I need to do my load step. I need to do my loads. So let's create another load collector. Sorry, a load collector for my loads. And let's talk about loads a little bit here because I think this was a place that also confused a lot of students. So in reality, the final part, we're putting a steel block on the top of our part. And obviously, the load machine is pushing on the steel block, and that steel block is going to distribute that load over whatever area it is you have left in your design, whatever width it is. We don't know what that width is. So ultimately, you're going to, in solid modeling, that's a pressure. So if you look at loads, I have pressures here, I have forces, and I have moments. And so ultimately, that's a pressure. So I can click on pressures. And the way I've sectioned this up, I can actually, instead of picking elements, I want to pick faces. And I can nicely pick these faces because they're nicely sectioned for where that pressure is going to go. So we're going to go ahead and accept that selection. And I can apply, in this case, it would be 18,000 kilonewton or 18,000 Newton. So I'm just doing a little calculation here. So 18,000 divided by 25, divided by 50. And I get 14.4 MPa. So it's got 14.4 MPa of pressure. Now, I could do that. One of the problems with doing this early in the design is that I don't know if it needs material all the way out here at the edges. I've just created a design space, but yet I've loaded it. And if material doesn't want to be there, then there would be no load there. And so at this point in the design, I don't think that this is the best way to model this. However, at your final design, this is clearly the best way to model it because now then you'll know the exact area that you'll have. But at this point in time, we don't know the exact area. So doing the pressures this way, or doing it through a pressure at this point, I think is, again, not the best. You could do it this way. There'd be nothing wrong. I wouldn't take off anything. I would just comment that it might not be the best way to do it at this point in time. So if it were me doing it, let's just go ahead and delete this. So I'm going to select loads. This is your selector. I'm just going to go ahead and select all these loads because they're easy to select. Make sure you didn't select anything underneath it and just hit the delete key to get rid of them. This is still my current load collector, so I'm still creating things in here. I'm going to create forces instead. And I'm going to create forces right down the middle because clearly material must exist at the middle because if material didn't exist at the middle, well, the only thing is that it could exist at either edge and not the middle. But I'm going to say, okay, well, material kind of probably has to exist at the middle. So let's just put all the load at the middle, and that way it gives it an opportunity for the edges to go away. I'm not loading anything on the edges. So I'm going to pick these nodes by path again. And the first thing to realize is I think I have 10 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means I have 11 nodes. And so I need to divide that 18 kilonewtons or 18,000 newtons by 10, which is 1,800 newtons. And I need to apply the 1,800 newtons over the interior nodes. Okay, so I got 1,800 newtons in the minus z direction. And then I need to apply half of that on the exterior, on either side, because either side gets half because it doesn't have an element on the other side to take it. So that would be 900. Okay, that's exactly 18,000 newtons. Okay, so that's how I do it. But again, it's a little bit of it is engineering preference. Neither one of them would be completely wrong or right at the same time. Okay, let's create a load step. So now we're going to create a load step to combine these. I call it bending. We're always going to be starting with a linear static analysis. We need to pick our constraints as the SPCs. We need to pick our loads as the load, and that's the minimal you have to do. Everything else doesn't need to be picked, and I've got my linear static load step defined. Okay, then we need to ask for some control cards, which is the output request in an output file format. To do that, we're going to right-click, create cards, and then output. It'll give me my global output request. We do displacement, stresses and strain. And then I want to specifically ask for a particular format. So if you just right click on cards and say create, you'll get this other output, which allows you to pick a specific format. The format that we want is H3D. You got to pick it twice. So make sure you pick it twice or a little bug. Okay, so I've gotten through all of that. Now I'm ready to export and solve. So let's first save this file. So file, save as, and let's save it as in a demo directory. I'm going to call it demo homework 4, and this is a analysis. So remember, we always prove that our model is working with an analysis before we go to optimization. So I'm saving this one as my analysis run, and I'm on the analyze tab, so I can analyze ribbon, so I can go over to just run my analysis. It'll spit out a .fem. You go ahead and say export it, and go ahead and run it. And you should see here in a second, this should run relatively quickly. Okay, so you can see here that it ran in that the max deflection was minus 4.21 millimeters, which makes sense, right? If this is 200 millimeters long, minus makes sense. It's going in the negative Z direction, and the magnitude makes sense, about 4 millimeters. So everything looks good so far. So first thing I look at. The second thing I look at, of course, remember to add your second page. I already added one. Go to your second page. Make sure it's a hyperview, which is the post processor. And then we want to open up the analysis results. So we say open, come down here, and make sure both of these are checked. And if you do, both of them are checked. When you load one model, it'll load both the model and the results. So you know the file we want is the .h3d file because that's where the results are. So we say open, it loaded in both the model and the results, and then I can say apply. So my model and my results came in. The second thing I look at is just global deflections, right? So I usually plot the magnitude of displacement just so I can see something colorful. And then I go to the deformation ribbon bar and I say, hey, show me the undeformed shape. And sometimes I'll make this, let's say 3 times bigger than it really is. So I can kind of exaggerate the movement and I can see indeed, and then I can play, the deformation. So I can see indeed it's sitting on this roller and this roller is not moving in X. But if you look at this one, you can see that roller is moving in X, which is exactly what I want, right? I want it to freely move, but is resisted in Z completely. And you can also see, if I were to look at that in the Y direction, that it's allowed to come in, or actually in this case, it goes out in the top a little bit, and it should come in. It goes out in the bottom too. So it's freely allowed to move, which is exactly what I was talking about. That it's just just Z restraint plus rigid body, and everything I did was just rigid body. So the X and the Y was just rigid body. It wasn't constraining anything in any other direction. You would see it kind of pick up a deformation or a kind of a concentration if you constrained it anything other than just rigid body. Okay, so I can stop that animation. This is just a good opportunity to say you can go through each kind of iteration this way. It's actually not an iteration because it's just a linear solver. It's just one, but it's just dividing the result by 25 steps. So it's not really an iteration. You can go right to the end. We'll talk about actual iterations when we get to optimization. Okay, so I'm happy. This whole process is just saying I'm happy with the model. So before you go on to optimization, make sure that there's nothing wrong with the model. Because when you get to optimization, if something doesn't solve in the optimizer, you don't want to be guessing, well, is it the model setup? Is it the optimization setup? What is it? So I've now at this point ruled out everything's working. So that means if something goes wrong in optimization, I've ruled out everything to do with analysis. It's all of that is working. So that's why we always perform an analysis first. Okay, well, now we're on to the optimization process. So this is, I forget, I think topic 16 or so, or what, I forget what topic it is. But you can, these are all on my lecture notes, these process slides. Ultimately, I want you to be able to build this just with these slides. It just is, and I still use these slides to this day, 30 years later, right? Because it's just a reminder, okay, I have to do these things. So what do we have to do to an analysis model to make it an optimization model? As we talked about, you have to do DRCO, design variables, responses, constraints, and objective. And then also remember that manufacturing constraints are on the design variable. So we have to add manufacturing constraints that are done on the design variable. So that's the process. Just always think DRCO. Okay, where do we do optimization? We do it on the optimization ribbon. And what you see here is design variables. So D are all right here. R, responses. C, constraints. O, objectives. So you're just working across this ribbon bar. The design variables we're creating are just topology right now. We're not creating any other kind of design variables. We want a topology design variable. I call it anything you want. I call it topo. And we want to do a topology design variable on a solid. And I have to pick my property, my solids property. Okay, that created all the design variables. Now, while we're here, you additionally create manufacturing constraints on the design variable. So I'm going to go ahead and create the manufacturing constraint that I want while we're here. And I want to draw direction constraint. So I know that I wanted to whittle away material in the Y direction. And so I'm going to do a split draw, which means that it can come at it from the positive Y and it can come at it from the negative Y. And how do I define that? Well, I define a vector that defines the Y axis, right? So you have to, and a vector is defined by 2 nodes. So my anchor node is here. And then, because it's right in the middle. And then I'm just going to go in the positive y-axis direction for my second node, and then I just pick the second node that defines that vector direction. Now the split means that it automatically created the negative one. Split says, okay, you define the positive one, I'll automatically create the negative one. And so I just defined that it has to whittle away material in the y direction. Okay, so that is just something that gives us a better result. Not sure how much I talked about that, but this you didn't have to do that for this. This is just my experience, and this will produce a better design. In general, I would study and learn over time, and including as we go on in the next several weeks, more about manufacturing constraints. There are several of these that are interesting, and I will play with them, especially extrusion, pattern grouping, especially symmetry, and maybe even overhang. So those are the ones I would talk. Oh, min dim. So min dim, stress constraint, draw direction, extrusion, pattern grouping, and overhang. So I would study those as we go through the course. That's not something you need to know right now. I'm not going to talk about every single one of them. I'm expecting you to do your own research in a master's graduate program. But I'm kind of saying, hey, these are ones to go look into. They're interesting, and you should be building many models and experimenting with these things. Once you have a model, just changing one thing at a time and seeing the result is actually very easy. So the point of this homework exercise was to get you a model so that you could start investigating some of these things. Okay, so that's a little bit of what I was intending as the class goes on, but not specifically for this homework. Okay, so I've got my design variables. Let me actually collapse all and then just expand the design variables just so it's clear that we created it. Now what do I need to do? I need to do responses. So I got a volume fraction. And the response type, when I hit the down arrow, I just hit V. It'll take me right to the V's, and I hit volume fraction and then close. And you can see my response came in. I also have another response for compliance. So I'll hit my response types, hit C, and select compliance and say close, and you can see my compliance came in. Then what's my constraints? My constraint is a volume fraction constraint. So the response that I want to constrain is the volume fraction response, and I want to make it an upper bound of 0.3. Or another way of saying this, keep 30% of the material, or another way of saying it is remove 70% of the material, whichever way you like to think about it. Either keep 30 or remove 70. They mean exactly the same thing. Okay, and my constraint came in here. And then I need to do objective. And what's my objective is minimize compliance. And I want to minimize, what is it I want to minimize? The response of compliance. And for what load cases? For my bending load case. Okay, and then my objective came in here. So I have DRCO completely defined. I'm ready to save this and run it. So file, save as. Save as a hypermesh model. We're going to save this instead of analysis. This is my optimization run. And I would probably even further clarify this run as with a draw split, just so I know what it is I ran. Because I might, just as an example, I mean, file management is something that is on you, but something I've learned that, naming the file something appropriate to the thing that I'm studying helps me understand all the, what I've done. Again, not required for this homework, but giving you tips as we go along while I'm doing this. Okay, so we've exported and solved, so now we're ready to export and solve. So on the optimized ribbon bar, you'll see we can run an optimization. So we hit the run button. It'll export right to the same directory where I saved this thing. We want to go ahead and export that, and then we want to run it. Now, this run, usually what I do, just to kind of watch it, is I wait for the first two iterations of the optimization engine to succeed, and you'll see them come in here, the first and then the second. And then I will plot a graph. So the first one came in. We call it iteration 0. It's basically the analysis over again. And then it'll do its second iteration, or iteration 1, which is its first optimization. So iteration 0, we call it 0 because it's just the analysis again. And then iteration 1 is its first kind of choice of densities. So now I can produce a graph. Once I have the first two done, and I'll put the graph over here. And it'll just kind of plot for me as this thing is progressing, the optimization is progressing. But what is it I want to plot? Well, I want to plot compliance because the objective was minimize compliance. So I should watch this curve continue to go down until it hits a minimum. So this is the curve that I watch to see if the optimization is progressing well. Um, so let me let it finish a couple of iterations, and then I'll pause the video because this takes about I think it takes about 10, maybe 15 minutes to solve completely. So I'll just pause to save video time, and then I'll come back on when it's finished, and we'll pick up again. Okay, so the optimization has finished, and a couple of things I just want to highlight. So it says optimization has converged, and that you have a feasible design. And so this is what you should see if everything went very well. You may see something else. It doesn't mean you might see an unfeasible design. Doesn't mean that it isn't a useful result, but it means that something happened and we need to investigate further. But you should see optimization converge feasible design. Also, you should see the compliance versus the iteration curve. And you can see that it comes down to a minimum, jumps up a little bit. What it's doing here is anytime you have a manufacturing constraint, it's raising the power of the density Young's modulus curve. Remember, I talked about a 0-1 optimizer, and we use a power law to relate the density to Young's modulus. So what it's doing is it's increasing the power law to make it more discrete, right? The higher the power law, the more that curve becomes a step function. And then it tries to find a minimum again, and then it increases the power law one more time, and then tries to find a minimum. So, you'll notice that compliance is lower than this one, but that's because it's a different power law. So it's perfectly fine. You'll see this 2 jumps. It'll do it twice. I want that to be clear also. Okay, so I just look at this curve. I should see a nice curve coming to some sort of minimum with 2 power law jumps. We can close out our curve. We can close out our solution. We can finish up with the post-processing. So how do we post-process optimization results? Of course, as always, we do our optimization on our second page, and we want to read in our design variable results. So all of the results in a topology optimization are in the underscore des.h3d, as we discussed in the lecture. So you want to post-process the underscore des.h3d. What does underscore des stand for? Design variables. What are the design variables? The design variables are the density of every element, right? Remember, a density of 1 means the material, a density of 0 means no material. So first thing I'll do is just show the element edges, and then I will plot the density. And I think a student here had an issue where it said, yeah, it only shows me 0.3 for everything. And that's because we're in a post-processing mode called an interpolation mode, which is what I was doing before, just dividing a single result by 25. But that isn't what we have. We have actual runs. We have actual number of runs. And so we need to go into what's called a transient mode. So when you go into the transient mode, you can then use these buttons to go through. Here's iteration 1, iteration 2, iteration 3, 4, 5, and so on. I could use the fast forward button to go to the very last iteration, which is iteration 35. That's the one where it converged on. That was my last number on that curve. So you should pay attention to the total number of iterations. I had forgot to mention that. In this case, it was 35. And you can also hit the play button. It will just play you what every iteration is doing as it's going through its optimization engine path. But I usually, of course, the one that you want to focus your time on is the last one. It's the converged one. It's the solution, the final optimization solution. And you can see here that density is somewhere between 0 and 1. And this is great. But what's hard about this view is that what I really want to do is all of the elements that have a density less than, let's say, 0.7, those are elements that are not there. And so I just want to remove, I want to tell the computer, I want to visualize this better. I want to remove those elements because it says these elements don't exist. And so the way you do that, once you have a contour plot of density, you have to have that first. Then you can go into an isoplot. And the isoplot will say, okay, I'm just gonna remove. So I think somewhere near it says show values above. So you just hit apply. And it'll automatically pick halfway through the range. So halfway is 0.5 automatically when you hit apply. So it's showing every element, only elements that have a density of 0.5 or greater. I normally look at things like 0.7 or greater. It didn't change much. And so to me, this is the design that it came up with. Okay. And what you see here is some sort of I-beam structure that has a top flange that curves down to the support. So that's very interesting. And a kind of a constant thickness shear web that maybe starts to have some kind of features in it, maybe. And then you can also see that, it in the width, the top flange and the bottom flange don't necessarily have the same width for the same length. And so these are just things that I take out of this. The dimensions don't mean anything yet. They're just features that you need to kind of think about that you want to put into a detailed optimization later. But this is as far as I want us to go in the homework to get a concept design. So I actually have a concept now, something that I can start kind of sketching and working from for a design that looks like it's some sort of optimal. Now, there are other concepts we can do with other manufacturing constraints, and that's where you'll get other concepts, and then ultimately kind of putting them all together into something kind of engineering creative actual design. But this is as far as I wanted you to go in the homework, and then I think I said submit me certain files, which you can see there. Okay, I hope this helped, and I will.